Hello, in this video, let's understand the fundamentals of the dynamic behavior of an inverter. So as we have discussed time and again, speed of the circuit is one of the key design parameters for a gate, right? And when you're designing, you need to employ the right kind of gates or choose the right architecture that ensure that the outputs faithfully change and in an acceptable time when the inputs change. So when we talk about delays in a system, we normally talk about two major kinds of delays. One is known as the contamination delay and one is known as a propagation delay. So any gate, if you look at it, or any piece of logic, if you look at it, there is a certain minimum time that is required for the Vout to transition when the input voltage changes. When you talk about delays, we talk about delay between a specific input to a specific output in case we have a system which has multiple inputs and outputs. So for every pair of input output, there exists a time which is the fastest time for the signal to propagate from the input to the output, and there is a longer time, right? So the contamination delay is the minimum time and the propagation delay is the maximum time. And while it is not very clear why the contamination delay is important, we'll revisit this again when we look at digital blocks as to how this impacts design or data flow in a long data path. So now let's look at a few aspects that need to be looked when we're designing a circuit for speed. So let's first think of a few timing definitions, right? So let's assume that we have an input signal which has a pulse. So again, when we're dealing with digital signals, our inputs and outputs are normally pulses with specific transitions from the 0 to VDD. So let's assume that the red curve shows my input signal, and let's assume I've given this to some inverting logic. So the output signal gets inverted with respect to the input, right? And so if you look at the delays, you have two delays. You have what is known as the propagation delay when the output transitions from high to low. So when the input transitions from low to high, to the time required for the output to transition from high to low is known as TPDHL. And similarly, the other time is the time when the output transitions from low to high, and it is known as TPDLH, right? So this is the low to high transmission. And typically, if you look at the propagation delay, if you want to quote one specific number for the propagation delay, we normally quote it as an average of the two. So here, if you look at the definition of the propagation delay and both for the HL and the LH transitions, you see that we are measuring this at VDD by 2, right? So we need a reference voltage. So we're looking at the time delay when the input is at VDD by 2 to when the output is at VDD by 2. Now this VDD by 2 is chosen because in CMOS, the output is a rail-to-rail swing, in the sense that the output of the CMOS has a lowest VOL of 0 and a VOH of VDD. And hence we can pick our transition point to be VDD by 2. In case you design another digital technology where there is not a full rail-to-rail swing, in that case, this transition voltage is decided to be the average between VOH and VOL. We also talk about two other times when we discuss, and that is basically what is known as rise time and fall time of the signal. So rise time of the signal is typically defined as the time required for the signal to rise from 20% of VOH to 80% of VOH. And similarly, we talk about a falling delay, and the falling delay is defined when it falls from 80% to 20%. Now let's look at something which is known as a timing analyzer. Now this is tools which are generally available during design, and these tools are used to check for timing violations. So remember, in any circuit, nodes can be classified either as input nodes, output nodes, or intermediate nodes. And if you look at every gate in this circuit, every gate in this circuit will have a certain propagation delay, right? And so this is typically 30 units of time is the longest it requires for the output to transition when any of the inputs transition. So remember, 30 is the longest for any given transition, right? So similarly, we'll see later in the videos that certain gates are slower than certain other gates. And so if you have to design a particular data path, sometimes you're biased toward choosing a certain gate over the other. If you look at the arrival time at any internal node, right? The arrival time at any internal node depends on the arrival time at the input and the propagation delay of the gate that connects that input to this internal node. So let's look at this case where we have three inputs to this very simple circuit, and the three inputs arrive at say 20 units after the time starts. I1 arrives at 30 units of time after time starts, and I2 arrives 50 time units after time starts. Now this means that the output of the first gate is going to be reliable, or it's going to be available only after 60 time units, right? So since A1 or since I1 is arriving late, that is going to decide when this intermediate node is going to be ready. Similarly, this intermediate node, since there's only one input and one output, going to be ready 20 units of time after A3. And finally, you have the output of the circuit, which is going to be ready after 110 units, and that's because even though this signal is ready, this gate will give a reliable output only after this signal is ready, and then you give it 30 units of time to process the data. So the analyzer to check if the output is ready by arrival time. Now there can be a requirement of when this output should be ready. So this analyzer will make sure that to check and see if you've designed the right circuit to meet the arrival time requirement. So when you do design, we talk about something known as a slack, and especially when we talk about timing, we talk about slack. And what is slack? Slack is the difference between the required time that an input or output should be ready to when the actual arrival time happens for that particular node. And we say that if there is a positive slack, that means that the circuit meets the timing constraint. So you can look at it in two ways. Either you say that you have a safe design and that you're meeting the arrival time, or you can say that there is room to improve. A negative slack, on the other hand, is a problem, because a negative slack indicates that the circuit is not fast enough, which means that either you need to employ some other different logic or slow down the time budgeted for that given block so as to meet the requirements. This is again a very simple first order analyzer that I've shown here. So other factors which may limit or which may determine the timing at the output can be related to things which have not been considered in this very simple analyzer. Something like the rising and falling delays of individual gates can be different. And then there is also something which is known as the input effect on the delay. That is, certain inputs take longer to process than certain other inputs. So all these things play into the output of the analyzer. So all these things need to be taken in carefully when you're analyzing for slack in a given circuit. Now, if you think about any system, a system can have multiple logic paths, and most of them we don't really need to do any special design, but most of them are fast enough and meet our timing requirements. So many a times optimization for timing boils down to a few critical paths in design. So these are the paths which have the longest, if you will, delay in the circuit, and these paths limit the operating speed of the device. So by optimizing these critical paths, you are able to meet the timing requirement or improve on the timing performance. So again, when you think about timing optimization, there are different abstractions where timing optimization can occur. The first one is at the architectural level, and this requires knowledge of the algorithm, how many gate delays can fit into a clock cycle, speed of memory, propagation along long wires, etc. So there is an optimization that can occur at the architectural level. Similarly, another optimization can occur at the logic level, and this would include thinking about what are the functional blocks we have, what is the kind of adder, what are the fan in fan outs of the gates that we'd like to use, etc. Similar optimization can also occur at the circuit level, and this would mean choosing the right transistor sizes, looking at what is the kind of CMOS logic we'd like to use. So far I've touched upon only one basic CMOS design style, which is static CMOS. There are many other styles of digital design in CMOS, and we'll look at that in subsequent videos. And finally, there is a large part which depends on the layout of the device, right? So things like parasitics, especially when it relates to wire lengths, when it relates to capacitances at various nodes, those can heavily be determined by how your standard cell has been laid out or how your custom design has been laid out. And so a lot of time is also spent, especially in custom design, to ensure that your layouts are good and the layouts reduce the parasitic capacitance that occurs at intermediate nodes. Now let's look at the basic transient analysis of an inverter. So an inverter, basically what we do whenever we look at design or delay in design, we normally look at an inverter and we let it connect to another gate at its output. So generally we don't look at a gate in isolation, but we look at a gate which is loaded with another gate at its output. And we apply a pulse at the input and we want to measure the profile at the output node and then compare the two to measure the delay. Now in this graph, now if I look at this very simple inverter of two transistors, based on what we have discussed about capacitance modeling in the MOSFET, you see that there are multiple capacitances that come in when these nodes transition. So remember, V in is changing and similarly V out is changing, right? And so you have these multiple capacitances which contribute to the capacitance at these individual nodes. So the way we do it is we have to first identify which are all the capacitances that are critical and then look at their individual contribution. So because these capacitances are nonlinear and voltage dependent, it is not possible to develop a closed form expression. So we'll use a lot of approximations here, just like how we did in the inverter, to make sense of design. So now if you look at these capacitors, let me draw your attention to the capacitor CSBP, that is the source capacitance at the PMOS, that is connected to supply. So this capacitor essentially has no voltage change across it. Similarly, this capacitor, the source capacitor on the NMOS, similarly does not have any change on it. And so those capacitances are excluded from the load capacitance. So what we see is that the rest of the capacitors essentially are lumped to the output node. If you look at CGS and CGSP, CGSP and CGSN do not impact the output node. They impact the capacitance at the input node. But what we are looking at is the delay to the output. So these would impact the delay of the previous gate, not of this gate. What is included in this gate is the input capacitance of the next stage. So the gate capacitance of the next inverter falls as a part of this overall capacitance at this node, right? So determining the node capacitance of this node is very critical because that directly impacts the delay of the gate. In addition to these transistor capacitances, if we are driving a long metal line at this output, then there is an interconnect capacitance that is associated with this node. So if you look at the total node capacitances, it has transistor capacitances of the inverter whose delay we are measuring, the interconnect capacitance of the interconnect connected at the output node, and the input capacitance of the subsequent stage. So now if you look at what the circuit reduces to, the circuit essentially reduces to you having an inverter where you've lumped all the capacitances to the output node, and then this capacitance either gets charged up through the PMOS during the low to high transition at the output, or this charged up capacitor discharges through the NMOS during the high to low transition at the output. So the problem reduces to finding charge up and the discharge time of the capacitors are basically the delays of the gate. Now again, to simplify the analysis, what we do is we assume that the input waveform is a square wave with 0-second rise and fall. So it's an instantaneous. Again, these signals are hard to generate, but this makes our analysis quick. So we use that to get a flavor of how the gate behaves. So we'll talk about two currents, the PMOS current, which is the charging up current, and the NMOS current, which is a discharging current. So now let's review a little bit about charging and discharging of a capacitor. So let's say I have a capacitor and I've connected a current source to it. And this current source is a constant current source which is continuously pulling a current I from the capacitor. So if I want to now measure the voltage across the capacitor as a function of time, I can set up the equation of the circuit as the current flowing through the capacitor, which is C dVc by dt, is given by I. Or in other words, what I get is that the voltage across the capacitor changes as a function of time, and it is a linear function, right? So basically, if I connect a constant current source to the capacitor, I'm going to get a voltage drop that is going to be linear. And similarly, on the other hand, if I'm using a constant current source to charge up the capacitor, my charge up is going to be linear, right? And it's going to charge up till whatever time I'm charging up the capacitor to. On the other hand, if I think of charging up a capacitor through a resistor and a voltage source, right? So if I'm going to do a charge up in this fashion, then in that case, I use this is a first order circuit, right? So this is an RC network, it's a first order circuit. So I can write my RC dVc by dt plus Vc is the charge up voltage, in which case during charge up, I'm going to have a profile across the capacitor, which is an exponential rise. If I plot voltage as a function of time, my voltage initially increases rapidly and eventually saturates to whatever the charge up voltage is. Similarly, if I'm discharging this capacitor through the resistor, then essentially the initial charge drop is pretty significant and then it's asymptotically comes down to zero. So if you look at transistors, we will use both these models, but in most cases we will say that the transistor discharge and charge up looks like an RC network. And later on we'll develop an RC delay model for the transistor, which will be used to analyze for delays in digital circuits. In an RC circuit, as all of you know, this time is a very critical time, and this is known as the time constant of the circuit, and that dictates the speed at which the capacitor is charging up or the speed at which the capacitor is discharging out. So this time constant of the circuit RC is a very critical time constant in the charging and discharging profile. Now let's look at if you have an abrupt transition at the input, essentially what's happened is right at this time you applied VIN, and that VIN turns on the NMOS and that shuts off the PMOS because this VIN rises to VDD. So the NMOS turns on, the PMOS shuts off, and so this output node essentially has to transition from VDD to 0, and that discharge is going to happen through the current of the NMOS, right? And so if I look at the output profile looks something of this fashion. It looks like an RC, it is not an RC. Now, if I look at the delay I would measure is the difference. Again, this is a CMOS circuit, so I will measure the difference at VDD by 2. So the difference in times at VDD by 2 indicates the delay of the circuit, the falling delay of the circuit. The reason why I said that this looks like an RC but is not an RC is because the current in the NMOS, as we've looked at in the previous videos, the current in the NMOS is not constant during the discharge. This current changes as a function of Vout because Vout dictates the VDS of the NMOS, right? So initially when your gate is VDD and when your output is VDD, the NMOS is in saturation. But as the output voltage falls, the NMOS transitions from saturation into triode region, and then the current has a Vout component to it. Right? So keep in mind that during discharge, it's not always that the NMOS works like a current source. It in fact has a combination of a current source like discharge and a resistive discharge. So one quick way of measuring the delay, because we know that when we have a current source, life becomes very easy because it's a linear profile. So if I want to approximate this to a linear profile, then I'll assume that I will treat the NMOS as an constant current source which has an average discharge current as the average between these 2 points. And in that case, I can basically talk about an average discharge current and then calculate the delay of the gate. And so in that case, my falling delay, that is my propagation delay when the output transitions from high to low, is given by C load into VDD minus V50. So this is the net charge that I need to discharge from the capacitor, C times V. And this net charge that is discharged from the capacitor is being discharged with a constant current source of I average. So the delay is just given by charge by current. So this is a very simple but straightforward method of modeling the delay in the NMOS transistor and the CMOS. Similarly, for the rising transition at the output, we assume that the input transitioned abruptly from VDD to 0, in which case now your NMOS shuts off, your PMOS turns on, and in that case your output rises from 0 to VDD. So again, here what's happening is this NMOS is turned off. So the PMOS now functions as a source of current, and initially the PMOS has a large VSD, so it's going to be in saturation. As this voltage rises from 0 to VDD, the PMOS moves into triode region, and so you get again a combination of both a current source as well as a resistive kind of charge up. The delay again is measured at VDD by 2, and using the same logic as before for the NMOS, we talk about an average current between these 2 points, right? So the average current at the point when the PMOS initially starts charging up, which is when VGS is equal to minus VTD, VDS is also equal to minus VTD. That is, this node is at 0 and this node is also at 0. That is when the PMOS turns on and starts charging up this node, and it continues to charge till this node hits VDD, but we will be looking at only the transition up to V50%. So hence we look at the current when it rises up to V50, and in that case I can talk about my low to high transition as just the C load times the total charge I need to charge up the capacitor to divided by the current. So again, this is a very simple first order measurement of the delay, but this gives us very interesting insight into how we should design the inverter. So for example, let's assume that both zeros and ones are equally probable, right? So if we know that this node can either swing to 0 or 1 at any time, we probably want to design this inverter so that both the rising and the falling delays are equal, right? That is, there is no bias between a 0 or a 1. So if I want to do that, let's assume now that this C load is not related to the transistor sizes. That is, the C load is dominated by a very big interconnect which is connected at the output. And the reason I'm bringing this is because then this load capacitance is independent of the transistor sizing. So if we do that assumption, what we see is that if I again assume, like a symmetric inverter, if I assume that the VTs of the two transistors are close together, and if I assume that both the transistors, for example, are in saturation. So I'm making these very generic assumptions to give you a flavor of what's happening in the inverter. What you see is that if I want equal discharge and charge up times, I essentially want to ensure that the charging current is the same as the discharging current, right? So whatever the total current that is flowing into the capacitor during the charge up time should be equal to the total current that is flowing out of the capacitor during the discharge. And if I assume they're both in saturation, I essentially mean that the currents in saturation have to be equal for both PMOS and the NMOS, which tells you that the ratios of the widths of the PMOS and the NMOS have to be inversely related to the mobilities. So typically in silicon, what happens is that the channel hole mobility and the channel electron mobility are roughly related in the ratio of 1:2. That is, the electrons are twice as fast as the holes, which means that when we design inverters, we design them in such a way that the PMOS size is roughly 2 times the NMOS size. Now again, a note to keep in mind is this mobility ratio changes as a function of technology. What I've been quoting 2:1 is typically used in many textbooks and typically references technology in the long channel generations of a few microns. Over the years, the ratio has changed, and if you look at some of the recent NMOS PMOS ratios, they are pretty close to 1. So really this ratio depends on the technology that you're using, and generally when we design these, we design them such that the drive currents are equal. And so if you were to actually think about transistors where their velocity is saturated, then you'd have to use that model to come up with the relationship between Wn and Wp. So how would you speed up a circuit? Because that's essentially what we want to do, right? Many a times when you're designing a system, you want that system to respond as fast as it can. So first thing which is obvious to do is your design should reduce the load capacitance as much as it can, right? So whenever we are designing fast circuits, we want to ensure that our node capacitances are as small as possible. The other big hit we can get with is VDD. Suppose we reduce the VDD of this circuit, essentially means that the amount of charge that we have to build up into the capacitor and the amount of charge that we need to remove from the capacitor reduces, again, which means that we can switch the nodes faster. And the other option is somehow if we can increase the charging and the discharging currents, that way we can speed up circuits. So this is another reason why we choose the smallest gate lengths, right? Because when L is small, we expect the currents to be very large, and so those would speed up the transitions at the output for a given circuit. So to conclude, the inverter switching can be essentially broken down into a charging and a discharging process associated with the capacitor, right? And this is the capacitor that is connected to the output node of the inverter. Now the load at that inverter consists of multiple things. This output capacitor consists of some capacitance related to the inverter itself. It also comprises of interconnects which might be connected to the output node, and it comprises of the gate capacitance associated with subsequent gates that are connected to this node. So you see that the delay of the inverter really depends sort of on the environment it is in, right? Depending on what it is connected to and depending on how it is connected to the next stage, the delay of the inverter will change. And then once the model, we look at a couple of models to think about delays. Once the delay model has been understood, then we can look at technology options or circuit options to speed up such a gate.